Bismillahir-Rahmanir-Rahim and Assalamu alaikum to you all. On behalf of DHA Education System, I welcome you all in my computer science class. Course code is 2210. In week 5 for class C2, format of this session will be carried out by taking review of the topics covered in week 4, that is computer ethics. After that, we will discuss topics to be covered in week 5 and we will also discuss their learning objectives. Students, as you all know, we have completed all syllabus from book 1, that is majorly based on theory except few numerical content. So at this point of time, I am not going to start syllabus of book 2, rather will reinforce the numerical part of book 1. So I will reinforce interconversion of number system from chapter number 1 in today's lesson. We will practice 2 questions from past papers and in the end an assignment which is purely based on past paper will be given that you can download from DHA portal to solve. In week 4, we discussed about computer ethics. Computer ethics is a set of principles set out to regulate the use of computers. Or we can say computer ethics are a set of moral standards that governs the use of computers. There are some common issues related to computer ethics. That includes intellectual property rights such as copyrighted electronic content, privacy concerns, and how computers affect society. For example, while it is easy to duplicate copyrighted electronic or digital content, computer ethics would suggest that it is wrong to do so without the author's approval. Intellectual property is further categorized in 2 branches, namely industrial property, which broadly speaking protects inventions, and copyright, which protects literary and artistic work. Copyright laws protect intellectual property, which includes literary and artistic work such as novels, poems and plays, films, musical work, artistic work such as drawings and paintings, photographs and sculptures, etc. Then we talked about netiquettes. Netiquettes are about the various risks related to using the internet. It is about proper ways in which to use a network and to determine whether information is reliable. Then we talked about plagiarism. Use of internet has led to an increase in plagiarism. This is when a person takes another person's work or idea and claims it as their own. However, some software exists that can scan text or then look for example of plagiarism by searching web pages on the internet. And last, we talked about 3 applications, namely free software, freeware, and shareware. These 3 applications can be downloaded freely from the internet and can be used. Free software, in which users have the freedom to run, copy, change, or adapt free software. For example, Photograph Manager, F-Spot, similarly desktop publishing softwares, and Abbey Word, which is a word processor software. So essentially this sort of software can be run for any legal purpose. It can be shared with family, friends and colleagues, and also we can change the source code of this particular software. Then we have freeware. Freeware is a software a user can download from the internet free of charge, and once it is downloaded, then there is no fee associated with using this particular software. For example, Adobe, for example, Skype, and Media Player, and many other freely available softwares. Lastly, we discussed about shareware. In this case, users are allowed to try out some software free of charge for a trial period. At the end of the trial period, the author of the software will request that you pay a fee if you like it. So to get register, the user has to get the registered version, the user has to pay for that particular software. So that is it for chapter number 8. In week 5, we are going to reinforce the numerical part of chapter number 1. That is interconversion of denary, binary and hexadecimal numbers. Then we will solve 2 questions from the past papers. By the end of this lesson, students, you should be able to describe the purpose of number systems, elaborate conversion methods, recall concept that you are going to learn in this lesson and that you have already learned in class C1. And by the end of this lesson, you will be able to practice questions from past papers individually. Number system is the basic part of chapter number 1. The system of counting and calculating is called a number system. In the context of chapter number 1, there are 3 categories of number system: denary, decimal number system, binary number system, and hexadecimal number system. The number system, which is based on 10 characters from 0 to 9, is called denary or decimal number system. For example, 75 with base 10 is a decimal number system. 75.5 with base 10 is also a denary number. Minus 75.5 is also considered a denary or decimal number system. Decimal number systems are used to represent various sort of physical quantities. For example, current, for example, weight, for example, temperature, etc. The number system, which is based on 2 characters 0 and 1, is called binary number system. For example, 1000011 with base 2 is a binary number, or 110.11 with base 2 is also said as a binary number. So any number with a combination of zeros and ones with base 2 is known as binary number. Binary numbers are used to represent electrical states of current or voltage as on or off. So on is said as 1 and off is said as 0. The number system, which is based on 16 characters from 0 to 9 and from A to F, is called hexadecimal number system. For example, 4FA with base 16 is a hexadecimal number system. Similarly, 5T is a hexadecimal number system, and if I say 43 with base 16, that is also a hexadecimal number system. Hexadecimal number systems are used to represent color codes in HTML. They are used to represent MAC addressing. They are used to represent mnemonic or operation code in assembly language. They are used to represent memory dump, to locate errors, and they are used to debug those errors. This diagrammatic representation is quick and easy way to recall which method will be used to convert one number system into another number system. For example, if you are given a decimal number system and you are asked to convert it into an equivalent binary number or into an equivalent hexadecimal number, then you will be using the remainder method. If you are given a binary number and you are asked to convert it into an equivalent denary or decimal number, then you will be using expansion method with binary notation. And similarly, if you are given a hexadecimal number system and you are asked to convert it into an equivalent denary or decimal number system, you will be given expansion method with hexadecimal notation. Lastly, when you are given a hexadecimal number system and you have to convert it into an equivalent binary number system, or a binary number system is given and you have to convert it into an equivalent hexadecimal number system, you will be using 4-bit BCD table or 4-bit binary notation. That is the table 1.2 in your book. So this is the interconversion number system chart that may help in converting number from one number system to another number system. Binary to denary conversion. To convert a binary number into an equivalent denary number, we will be using binary notation or expansion method. For example, we are having a binary number 1001111. We will multiply each bit of this number with its binary notation. We'll multiply the number with its binary notation. We'll add all them together to get an equivalent denary number. On the contrary, we have another shortcut method. We will be writing the question as a binary value. We will put the binary notation, that is 1, 2, 4, 8, 16, 32. Then we will ignore the notation under the 0 bit because those are the off bits. And we will add the remaining numbers. So we will be adding the binary notations of the on bits. So here we have 32, we have 4, we have 2, and we have 1. These binary notation have the values on values. So we will be adding these. 32 plus 4 plus 2 plus 1 gives us 39. So this way the number 1001111 is converted into an equivalent denary number, which is 39. To convert a denary number into an equivalent binary number, again we will be using binary notation. Binary notation is used to convert a denary number into equivalent binary number. For example, 120 is the given denary number that can be expressed in the binary notation. So we need to write the binary notation greater than till greater than 120. So the binary notation will be taking 1, 2, 4, 8, 16, 32, 64, 128. Because the given number is 120, so we are not going to write further binary notation 256 and so on. Put 1 under the notation which are required to find sum equals to the number, and then put 0 in the remaining places. So we will put 1 under 64, we will put 1 under binary notation 32, we will put 1 under binary notation 16, and we will put 1 under binary notation 8 to get an equivalent number, which is 120. So this is how you can convert a denary number into an equivalent binary number. To convert a denary number into an equivalent binary number, we have an alternate method that is known as remainder method. For example, we have a denary number 107 and we are asked to convert it into equivalent binary number. So we will divide it with 2. 107 when divided with 2, we'll write the quotient and remainder parallel. So we got 53 in quotient and 1 in remainder. Now we will divide 53 with 2. We will again write quotient and remainder in parallel. So we'll keep doing it until we get quotient lesser than the divisor, which is 2. In the end, we will read the remainder from bottom to top to get the binary number. So this is how a denary number is converted into an equivalent binary number. Before starting the conversion from hexadecimal to binary and denary, we need to understand the relationship between hexadecimal, binary and denary. So a table is given here. This table is given in your book. Since 16 is equals to 2 raised to power 4, this means that 4 binary digits are equivalent to each hexadecimal digit. So table 1.2 summarizes the link between binary, hexadecimal and denary. So in the table, the very first column shows the binary values and the next column shows the equivalent hexadecimal values and the next column shows the equivalent denary values. We need to see how these values are formed. If we just look at the binary values, these are the group of 4 digits. you need to put binary notation on these digits, and that is 1, 2, 4, 8. So you will be putting the binary notation from the extreme right side of the given binary digit. So for example, if we have the number 1011, we'll be putting the binary notation on it 1, 2, 4, 8, and we'll add those binary notation which is having the value 1. So in this way, we have 8 plus 2 plus 1, which gives us the result 11. So if you look in the table 1.2 at the value 1011, there is an equivalent denary value which is 11, and 11 in hexadecimal is equivalent to B. This is how this table is formed. We will be using this table to convert a binary number into the equivalent hexadecimal number and a hexadecimal number into the equivalent binary number. So you can use this table as the reference. Binary to hexadecimal conversion. While converting from binary to hexadecimal is fairly easy process. Starting from the right and moving left, split the binary number into the group of 4 bits. Then if the last group has less than 4 bits, you can simply fill in with zeros from the left. That is not going to change the number but will complete the number. Take each group of 4 bits and convert it into the equivalent hexadecimal using the table 1.2 that we discussed in the previous slide. So here we are given with the 2 examples. Example number 1, in which the binary number is given. First, we will split up this number into the group of 4 bits, and we'll start it from the extreme right side. So we have formed 3 groups here, and luckily all the groups are fully filled with the digit, so they are not less than 4 digits. So the very first one is 1011. If we put binary notation on this 1, 2, 4, 8 and add the binary notation which is having the value 1, we get the equivalent hexadecimal number which is B. For the next group, the number is 1110. If we put the binary notation on this number 1248 and we add the binary notation whose value is 1, that gives us 8 plus 4 plus 2, which is 14. And in table 1.2, you can see 14 is equivalent to E. And the last group, 0001, when we put the binary notation 1248 on this group, it is going to give us the value 1. So this is how we will simply convert a binary number into the equivalent hexadecimal number. For more clarity, let's solve another example. In this example, we are given a series of binary number. First, we will split up this number into the group of 4 bits. So we'll start from the extreme right side. We got 1, 2, 3, 4 groups. At the extreme left side, the last group is having 2 digits. So to complete this group, we will add 2 zeros in the start. Now we are going to give the binary notation 1248 on each of this group. And we'll be using the table 1.2, or we will be using the binary notation. If we do not want to use that table, we'll simply use binary notation. Otherwise, you can use the table 1.2, and from the table, you can find the equivalent values of hexadecimal. So 0010 will give you the value 2 from the table. 0001 will give you the value 1 from the table. 1111 will give you the value F from the table, and 1101 will give you the hexadecimal value D from the table. So this is how you can simply convert a binary number into the equivalent hexadecimal number. Now, if we are given a hexadecimal number and we are asked to convert it into the equivalent binary number, we will be using the same table or the same binary notation method. So the method is very straightforward. You will be using the table. Simply take each of the hexadecimal digit and write down 4-bit code which corresponds to the digit. For example, we are given with the hexadecimal number 45A. Using table 1.2, you can find the equivalent 4-bit code for each digit. 4 is equivalent to 0, 1, 00. You can see that from the table. 5 is equivalent to 0, 1, 0, 1. And A is equivalent to 1, 0, 1, 0. We'll put the groups together to form one binary number. If you do not want to use the table 1.2, you can simply use the binary notation 1248. So you will be writing 1248, and to make 4, you will put 1 under the binary notation 4, and you will make rest of the binary notation 0. To get 5, you will put 1 under the binary notation 4 and under the binary notation 1, and you will put rest of the places 0. And to get A, which is equivalent to 10, you will be putting 1 under the binary notation 8 and under the binary notation 2, and rest of the binary notation will be considered as 0. So this is how you can get equivalent binary number. There is another example, BF08. Again, you can just use the table and simply from the table see the binary value of the B and write it down. See the binary value of the F, which is 1111. See the binary value of the 0, which is all zeros, and the binary value of the 8, which is 1000. Then put all the digits together, and this is how the hexadecimal number is converted into the equivalent binary number. To convert a hexadecimal number into the equivalent denary number is fairly straightforward. Take each hexadecimal digit and multiply it by its value. Add the totals together to obtain the denary value. Look at the following two examples to see how this works. For example, we are given with the hexadecimal number 45A. First, multiply each digit by its value. 4 will be multiplied with its hexadecimal notation, which is 256. 5 will be multiplied with its hexadecimal notation, which is 16. A is equivalent to 10, so 10 will be multiplied with 1. We'll multiply it all and then add the totals together, and we are getting the equivalent denary number this way. There is another example. We are given with a hexadecimal number C8F. First, multiply each digit by its value or by its hexadecimal notation. So 12 will be multiplied with 256. 12 is the value of C in hexadecimal table. Then the next digit 8 will be multiplied with 16, which is the hexadecimal notation, and then the last number F is multiplied with 1, which is the hexadecimal notation. Add the totals together, and this is how we get the equivalent denary number. Now I will explain the last conversion of this chapter, which is from denary number to equivalent hexadecimal number conversion. This method involves successive division by 16. The remainders are then read from bottom to top to give the hexadecimal values. For example, if we are given with a number 2044 and we are asked to convert it into the equivalent hexadecimal number, we will be using the remainder method. We will divide the number with 16. We'll keep on dividing it. We'll write the quotient and the remainder in parallel, and we'll divide it till we get the quotient lesser than the divisor, and in the end we will collect all the remainders from bottom to top. So we got here 7, 13, 4 as remainder. 7 will be written as it is. 13 in hexadecimal is equivalent to D. So we'll write D instead of 13, and 4 will be written. So 2044 denary number is equivalent to 7D4 hexadecimal number. To get the grip over the concept that we have revised, I have taken a question from past paper year 2016. Question paper variant is 1-1. This is question number 7. It says, each seat on a flight is uniquely identified on an LCD above the seat. For example, seat 035C is shown as this way. So 035C is shown this way. The first 3 characters are digits that represent the row. The fourth character is the seat position in that row. This is a single letter A to F that is stored as a hexadecimal value. Each of the 4 display characters can be stored in 4-bit register. For example, 0 and C would be represented in this following example. So 0 and C, their binary values you can see. In the 4-bit register, we have put a binary notation 1, 2, 4, 8 here. So recall the method when you are given a hexadecimal number and you have to convert it into an equivalent binary number, then you were using 4-bit BCD table or the 4-bit binary notation. Okay, as in the first row we want 0, so all the bits will be make 0. While in the second row we want C. C in hexadecimal is equivalent to 12. So to make the value 12, we need to turn on the bits whose binary notation when added together give us the value 12. So we know 8 plus 4 makes 12, which is equivalent to C. So we have put 1 under the binary notation 8, and we have put 1 under the binary notation 4. This way we got the equivalent value of C. Now the A part asks us, show how the 4-bit register would store the remaining 2 characters 3 and 5. So we need to use here again the binary notation. So we'll put binary notation here 1, 2, 4, 8, and to get the value equivalent to 3, we will put 1 under the binary notation 1, and we will put 1 under the binary notation 2, and we will make rest of the binary notations as 0. So this is how we are going to get the answer 3. To get answer 5, we will put 1 under the binary notation 4, and we will put 1 under the binary notation 1. This is how you're going to get the answer that is equivalent to 5. So let's see now the answer. So 3 in binary notation is equivalent to 0, 0, 1, 1, and 5 is equivalent to 0, 1, 0, 1. So this is how you can easily comprehend the example given in the question and solve the question easily. Now let's see what it asks to do in the B part. Identify which seed is stored in the following 4-bit register. Here we are given with 4 different registers in 4 different rows. So we are going to get an equivalent hexadecimal value for that. So for that matter, we need to put binary notation. So when we are going to put the binary notation, we need to see the on bits. So here on bit is 1 and rest of the bits are off. So here we'll write 1. In the second row, the binary notation 8 and binary notation 1 will be added, and we will get answer 9. In the third row, the binary notation 4 is the answer, and in the last row 8 plus 4 plus 2, we are going to get the answer 14, which is equivalent to E. Now let's see the answer. Yes, we got, for the first row we got 1, for the second row we got 9, for the third row we got 4, and for the last row we got E, which was equivalent to 14. So this is how a number which was a binary number is converted into an equivalent hexadecimal number. You can also see the mark division. The first 3 rows consist 1 mark and the last row consists 1 mark. So this is how you can get 2 marks. Now let's take another example. This is question number 3 from paper May-June 2016. Question paper variant is 1-2. It asks us to convert the following hexadecimal number into 12-bit binary. So the hexadecimal number given is 4AF. So there are 3 digits. So 1 digit will be stored in 4-bit binary, and the next digit will be stored in 4-bit binary, and the next digit F, that will be stored in 4-bit binary. So collectively that is going to make 12-bit binary register. So we are going to put the binary notation on each 4-bit register. So this is how we are going to put binary notation. So we'll start from the left. To make the first register 4, we will be turning on the values. Yes, to make it 4. Yes, this is how we are going to get the answer 4. We will put 1 under the binary notation 4 and make rest of the bits as 0. Okay, then to get A we know is equivalent to 10 in hexadecimal number. To get 10, we need to turn on 8 and 2 binary notation. So we will be putting 1 under the binary notation 8 and under the binary notation 2. So this is how we are going to get the value A. Next, to get the value F, we know that hexadecimal F is equivalent to 15. So to get answer 15, we need to turn on all the binary notation. So 8 plus 4 plus 2 plus 1 makes 15, which is equivalent to F. This is how this question will be solved. Now you can see the marking scheme when we will be writing all the bits collectively. That is going to give us the answer. So 1 mark for each nibble. Nibble means 4 bit. So this is how you can score 3 marks. Now let's solve the B part. The 2016 Olympic Games will be held in Rio de Janeiro. A timer that counts down to the opening of the games is shown on a microprocessor-controlled display. The number of hours, minutes, and seconds until the games open are held in 3 8-bit registers. The present register values are given in this register. You can see 105 hour. The value of 105 hour binary is given in 8-bit register. Then 32 minute is given in 8-bit register. And then 20 second is given in 8-bit register. The timer will count down in seconds. Now we need to focus upon this term count down. Countdown is, for example, if you want to count down from 10, so 10, then 9, 8, 7, 6, 5, 4, 3, 2, 1. This is how the countdown goes on. In part 1, it asks, show the values in each 8-bit register 30 seconds after the time shown above. Now we need to count down 30 seconds. It basically means that we need to subtract 30 seconds from the given time. But 30 seconds cannot be subtracted from 20 seconds. So we know that to get the binary values of the hours for the minutes and seconds, we use binary notation or the expansion method. But let's do the working first. We were given 105 hours, 32 minutes and 20 seconds. We need to count down 30 seconds. So to subtract 30 from 20 doesn't make sense. So if we write minute in this way, minute 32 minute is equivalent to 31 minute 60 second. Now if we just add this 60 second with the 20 second, we get 80 second. Now we can easily count down 30 seconds from 80. So 80 when subtracted with 30, we get 50 seconds. So we got the answer 105 hours, 31 minutes and 50 seconds. Now we need to write the binary values of these in this 8-bit register. So the value of R will remain same, that is 105. The value of minute, which was 32 initially, but now is changed to 31. So its binary conversion will be changed also. And the value of second, which was 20, now it is 50. Its binary conversion will be written in this 8-bit register. This is how this question will be solved. Now in the second part, it asks us, write the decimal value of minutes register from part B in part 1. Okay, the value of minute was 31. So if we just get the value 31, the binary value 31, and divide it into the group of 4 bits, we get 2 groups. One group that you can see in this red color. So this is the same 8-bit register. We have divided it in 2 groups. So one group is giving us the binary value 0001 and the other group is giving us the value 1111. When we have a binary number and we need to convert it into the hexadecimal number, we use 4-bit binary notation. So we will be putting 1248 on this group and 1248 on the next group. So in this way, we are having the value 1 for the first group and F for the second group. So this is how this question will be solved. Now let's see its marking solution. So that is it. This is the marking solution. You can see 3 conversion in question B part 1, 1 conversion gets 1 marks, and for the second conversion you are going to get 1 mark. So this is how you are going to score the marks. This is the assignment to practice. These are the questions taken from the past papers. You can download this assignment from DHA portal to solve. Thank you so much for your attention.